Now let's take a look at more applications of vectors, a tension problem. And you might have seen something like this in physics class before. A 500 Newton box. So that means that represents the force that is pulling down on the box. That's its weight, rather than expressing it in terms of mass, like you might be more familiar with, like kilograms. We're indicating in terms of weight, in terms of the force being exerted on the box. So a 500 Newton box is suspended from two cables that are attached to the ceiling at 45 degrees and 37 degrees to the horizontal. Express answers to the nearest tenth of a unit. Let's make sure we remember to do that. So, tenth of a unit. So watch your rounding at the end. We are assuming that these cables have an equal tension to them. Let's go through our steps and see what the best way is to deal with this. So, first of all, step one, we're going to set up our diagram like I've mentioned in the past. So set up our vector diagram. Step two, we're going to find our missing angles. And that's just basic trigonometry or geometry like you've done before since grade 9. And then in this case, we're going to be able to use sine law to find T1 and T2. So basically in this question, they're asking us how much force is each cable experiencing, or how much is each cable pulling up on the box against gravity. Let's sketch our diagram here and see what's going on. So I'm going to have 2 points here, and my box is going to be here. And the box is experiencing a force downward of 500 newtons. Let's draw our wires. Let's label these T1 and T2, and my angles here from the horizontal are going to be 45 degrees and 37 degrees. We know that the box is not moving, so we call this a static problem. The forces are static. Everything is at equilibrium. The force upward and the force downward are equal to each other. Do we know anything else about this situation? Not right now, but there are some things we can find out pretty easily. For instance, let's find our angle down here at the bottom. I know the sum of angles in a triangle is equal to 180. So off to the side here, and we can just label this theta to have some notation here. Theta is equal to 180 minus 45 minus 37. So theta is going to have a value of 98 degrees. And we can label that right away. All right, next I want to focus on this by looking at the box specifically. So I'm going to have the box here. And I know that if it's experiencing 500 newtons of force downward, in order to stay in the same position, it is also experiencing 500 newtons of force upward. And I know that each wire is pulling upward. So the T1 vector is going to be pointed in this direction, and the T2 vector is going to be pointed in this direction. If I add these vectors up, I'm going to equal exactly 500 newtons of force in the upward direction. So I can add these vectors here. So I can have vector T1, and I can have vector T2. The box is not moving left or right, so I know the y component of each vector. So the x component of each vector is going to cancel out. So these amounts are going to be equivalent. And I know that the x, or the y components, the height of each vector, so to speak, is going to add up to 500 newtons. So this part and this part are going to give me 500 newtons. Those labels aren't helpful right now. Like, I'm not going to leave them up there, but just to explain quickly what we're going to be doing here. All right, what else do I know about my angles here? Well, I know that the angle on T2, that this value right here is 37 degrees. So now I want to find the value inside the triangle here. So these are going to be complementary. They're going to sum to 90. So 90 minus 37 gives me 53 degrees. So in here I got 53 degrees. Same thing down here. I know the angle that T1 makes with the horizontal is 45 degrees. So that tells me that this value right here, I can figure that out pretty quickly, is also 45 degrees. And do I know anything about the angles inside? Yes, I can use my alternate angles. If this angle here is 37, then so is this angle here. So let's label that right away. Switch up the color to make it a little more distinct. That's going to be 37 degrees. And we can do the same thing on the other angle. If this is 45 degrees, so is this. So let's label that 45 degrees. So my angle here is 37 plus 45, which gives me 82 degrees. And I know it's a lot of little pieces to put together, so these are all rules that you're familiar with, but applying it in this new context, I know can be a little challenging sometimes. So let's think about what we know about this triangle now. I know all the angles. I know my angle up at the top here inside is 53 degrees. I know my angle here on the side is 82. I know my angle at the bottom is 45. And I know the side length here is 500 newtons. So I have a triangle where I have a pair of information. I have an angle and the side length across from it. And I have my other angles. So I can use sine law to find my missing values here. Let's go ahead and give that a whirl. For T1, so side length T1, the opposite angle is 53 degrees. So I'm going to have T1 over sine 53 degrees is equal to 500 over sine of 82 degrees. We can rearrange and solve fairly quickly. I'm not going to show all my work here, but I'll just talk it through. 500 times sine 53 divided by sine 82 gives me a value of 403.2 newtons. So T1 is approximately equal to 403.2 newtons. So I know the magnitude of that vector. And let's find T2. The angle across from T2 is the 45 degrees. So T2 over sine 45 degrees. And the same second half as last time equals 500 over sine 82 degrees. Once again, I'm just going to talk through the rearranging. I'm not going to show it all. So T2 is equal to 500 times sine 45 degrees divided by sine of 82 degrees. And we get a value there of approximately 357.0 newtons. And I think that's all we had to do. Technically, the question wasn't complete. It didn't tell us what to do, but what we actually had to do was find the tension in each wire. So, therefore, the tensions, the wire tensions, are 403.2 newtons for T1 and 357.0 newtons for T2. And the key idea here, just to be clear, I might have glossed over it a little bit, is that this is at equilibrium. So all x components cancel. So however far it is being pulled to the left, it is also being pulled to the right, so it's not moving left or right at all. So this, I'm just going to label this quickly here. On T1 here, this x component here, and on T2, this x component here, have to be equal and opposite to cancel out. I'm going to erase that so I don't clutter up our drawing too much. And same thing with the y components. The box is not moving up or down. So whatever force it's experiencing downwards, which we're told is 500 newtons, it must be experiencing upwards, and that's going to cancel out. So that's the key idea for questions like this. It's a static problem. That means there are forces in play that are canceling each other out. There's no movement. If it was moving, it would be a kinetic problem, and we don't have to deal with that here. And so we can use that information to create our vector diagram over here, use our basic knowledge of geometry and trigonometry to find our missing values, and then use our tools that we're familiar with, such as sine law, to solve for missing sides and ultimately answer the question. In our next question here, we're going to talk about defining vectors in terms of other vectors. So in trapezoid ABCD, sides BC, or sorry, side BC or line segment, whatever. Side BC is parallel to side AD. So BC here and AD here are parallel. That's what that symbol means. So they have the same slope. They travel in exactly the same direction, or because we're talking about vectors, we can say that they are collinear. And and AD is equal to 3 times BC. So the length of this, so if we took BC and repeated it 3 times, that would be the same thing. So we know the relative lengths there. Let vector AB be equal to U, and let vector BC be equal to vector B. Express vector AD, BD, and CD as linear combinations of U and V. So these are already labeled here. We can see that vector AB, U is right here, and BCV is right here. First thing we are asked to express, we'll break this into segments here, is vector AD. What do I know about vector AD? Well, we already said that it's 3 times our vector BC here, so let's express that. So vector AD is equal to 3 times vector BC, and because we've already told that vector A, or the length of AD, or of side AD, is equal to 3 times side BC, and we know that they are parallel or collinear, so the direction's the same. We're all good there. And we already said that here vector BC is equal to vector V, so we can just write this as 3 times V. So vector AD is equal to 3 times vector V. That was pretty self-evident. That wasn't too bad, I don't think. Hopefully you're able to follow through with that logic. Let's try our next one. Let's take a look at vector BD, which is right here. Try to make sure the heads of my vectors are nice and clear. Well, what do I know about BD? Well, it's equivalent to any combination of vectors that starts at the same point and ends at the same point. So we could think about it as a combination of BC and CD, but I don't know anything meaningful about CD, so that's not really helpful right now. Or I can think about it as equivalent to vector BA, remember the direction matters, plus vector AD. So let's write that out. Vector BD is equal to vector BA plus vector AD. And notice that we start at B and end at D. We start at B and end at D, and we kind of don't care about what comes in between there. And let's just tidy this up. I want to try to keep this uncluttered so you can just focus on the important part at one piece at a time. So what do I know about vector BA? Well, vector AB is equal to U. We have that right here. AB is equal to U. We're going in the opposite direction. So remember, I just need to multiply my vector by -1. The length stays the same, but the direction changes. So vector BA is going to be equal to -1 times vector U, or negative vector U. And we have to deal with vector AD, and we already talked about AD in the previous question. So vector AD is just equal to 3 times V. So that wasn't too bad either, because we've already talked about these things and where to find them. Finally, let's deal with vector CD. Once again, I don't know anything about CD specifically, so I'm going to go from here to here. Don't really have any helpful information, but what I can do is I can go from vector C to, from point C to B, and that's helpful because I see that has a length of V, but in the opposite direction. So vector CB is going to be -V, and I can go from B directly to D, and I just found that vector in the previous question. So let's do it up. Let's represent CD as a combination of other vectors that are being added together. So I'm going to have vector CB, and I'm going to have vector BD. What do we know about CB? I just said that over here. It's equal to -V. What do we know about BD? We just defined it in the previous question. just gonna erase my highlighting there for a moment. So sorry, we said that CB was equal to negative V plus our result from our previous question here. So negative U, negative vector U plus 3 times V. Let's tidy that up and collect our like terms. So negative V minus U plus 3V. Our like terms are vector B, so we're going to have negative 1V plus 3V is 2V minus U. All right, so we have successfully represented our various vectors here in terms of vector U and vector V. And there's no real conclusion here. It wasn't a word problem. It just asked us to express things in terms of other vectors, which we have successfully completed.